Okay, so I think we can start. Oh, 40. We have reached 40. Okay, so yeah, I'll be using my notes only today completely. So that this is okay. So let me set a few things. Yeah. Okay, everyone. I think you can hear me and you can see me as well. So you can see my notes as well. So as per the schedule, we were asked. I was asked to discuss quantum algorithms. Okay, quantum algorithms with you people, right? So let me do that. Quantum algorithms. Okay, right. So algorithms is a steps or commands, set of commands which would help us to do some task. Okay, some execution task. As you can see, we had some intro to algorithms, that is Dutch algorithm. Okay, right. Dutch Joyce algorithm. Yesterday we had that slight encounter. Okay, right. So we will build from there today, right? Fine. So whatever we came across is Dutch Joyce algorithm. We did not get in detail, but we just encountered, right? So before going into any algorithms, there are a few things which we should know, right? I would write that before getting into these few important points or important facts we should know. Okay, right? Number one, let me tell you what is that number one point. Number one point, okay, when you try to observe a system or when you try to find what is system is made up of, what is system is having, what states it exists in, right? A simple example I can tell you: if you just take a hot glass of hot water, keep it on a table. So hot water temperature is above 60 degrees Celsius. The room temperature is, let's say, 30 degrees Celsius. There is a 30 degrees difference between hot water to the room temperature. Because of that, what happens? The hotness or the temperature of the water keeps decreasing as water loses its temperature to the surrounding. You can see the humidification of air around the glass, okay, because of the absorption of the temperature. Okay, as you can see, the state of water, hot water, is changing in time as time progresses. Okay, so we see the change in the state of the system as time progresses. So there we are making an observation by sending a light onto the system, and reflected light we just observe. Okay, right? Right. Now, here, when you try to observe a quantum state, okay, observation of a quantum state, okay, leads to destruction of the state. leads to destruction of the quantumness. I would say quantumness. Okay, what I mean is the system which was, let's say, example, let's say electron is in the ground state. I send a pulse of pi by 2 pulse. So electron was made to go through an oscillation. There a quantum superposition state is prepared. Okay, right? So the superposition state is a quantumness. Now I can make an observation on that quantum state. What observation? Whether the quantum state is prepared with 0 or 1. Catch. Okay, usually there is a basis on which any system is defined. Okay, for two-dimensional vector system, yesterday we saw I cap and j cap is a basis on which it is defined. Now here the basis is 0 ket and 1 ket. We want to find the system is prepared in this basis 0 ket or 1 ket. One question you can ask, what is the other basis? Right? For example, in a real world, we will express the currency in Indian rupees, or most common is US dollars. Okay? Whether the currency, the amount is expressed in dollars or in rupees is a two way of expressing the amount, the money. Okay? So here also there is another basis in which we can express the same quantum system. Another basis is using the same basis elements you can construct a new basis, which is a new basis you can construct, which is plus ket minus ket. We also encountered this yesterday. What is plus ket, by the way? 0 ket plus 1 ket divided by square root of 2 equal superposition. Minus ket is 0 minus 1 divided by square root of 2. Why they are bases? If you can see, the inner product between plus ket to minus ket is 0. Inner product between plus ket to plus ket is 1. Inner product between minus ket to minus ket is 1. So these properties are satisfied. So this is the basis. They're orthogonal, they're perpendicular to each other, or they're in a way their dot product is 0. Okay, and they are normal, their length is 1. If you just try to find the length of this vector plus ket, if you have to write down, which is 1 by square root of 2, 1 by square root of 2 length, minus ket is 1 by square root of 2 minus 1 by square root of 2. Okay, their length is 1, normalized to 1, and they're orthogonal. Plus ket and minus ket are orthogonal, means they're perpendicular to each other. Okay, so the now question is whether given quantum state is prepared in 0 ket or 1 ket or plus ket or minus ket, we have to find. Okay, for that you have to make an observation on the system. We have to see whether the system is made up of 0 and 1. Problem with observation is the quantum system going through observation gate, it is represented by a box with the meter needle. So this would lead the quantum state to fall into 0 or 1. Okay, so destruction takes place and the system goes to classical form, means it is strictly in one of the state. Okay, no more quantum, destruction of quantum. Okay, this is very, very important point. You should remember why the quantum systems goes from quantumness to classical form when I make a measurement. Okay, right? How do you create a measurement? The question is again, how to measure? Okay, answer for that question is, From the basis element itself, you can create a measurement tools. What are the measurement tools? Measurement tools are measurement operator. Measurement operator or a tool you can construct by saying M0 is a measurement tool, came out of outer product between 0 with a 0. I just earlier we have an inner product. What is the outer product? Outer product is the column vector 1 0 multiplied to row vector, which gives me what? Which is going to give me a matrix. Okay. Similarly, okay. Similarly, M1 is, okay, M1 is 1 cat is equal to 0 1 0 1 is equal to 0 0 0 1. This is also another measurement tool. Okay, right? Just a minute. Hello? Yeah. Right. So I can just create a measurement tools like this. 1 minute. Hello. Ma'am, we are working on it. We will send. Yes, ma'am. Today it will happen. Oh, thank you. Sorry for that. I had to take a call from ministry. So these are the measurement tools. So now if you see measurement tool acting on a quantum state, okay, on either side you have to multiply with a quantum state with inner product. What it gives you? It gives you alpha star beta star transpose, right? This is the transpose or adjoint multiplied by 1 0 0 0. Now alpha beta, which is going to give you what? It is going to give you alpha star 0 0 multiplied by alpha beta, which is absolute alpha square. See, the quantum state measurement is giving me the number. Okay, in which state it falls in, if you want to find. Okay, so you would be doing M0 psi, which is going to give you 1 0 0 0 alpha beta. Okay, so what you will get? Alpha 0, which is alpha into 1 0, which is alpha over 0 ket. Okay, and similarly M1, if you act on a quantum system, you would be getting, okay, you would be getting beta into 1 ket. See, now with what probability I am getting that particular quantum state is obtained by the first method, and where the system is falling is obtained by second method. Okay, so this is how the quantum system fall into one of the classical form when you make a measurement. Since it is probabilistic in nature, I'll make a several, let's say a few hundreds measurement and then find out in how many times it falls to 0, how many times it falls to 1. So 0 ket and 1 ket are the fixed basis elements or fixed states, which means they are, okay, which means they are a classical forms. Okay, so what is happening is when you just take a quantum system sent through a measurement gate, it has alpha 0 plus beta 1. Basically, it is suppressing one of the state and leading to the other state. Means the probability amplitude is actually nullified. The probability amplitude, okay, is put to 0 when you make a measurement for one of the case. Okay, so that is what yesterday we saw, right? The implications. Implication, if you just take, okay, take entangle system. Okay, entangle system. Entangled system is represented by, let's say, quantum system A and B, where both of them are entangled like this. Okay, what I mean is two friends become so close, even when they're separated, they're going to have same effect when something happens to one of the guys. Okay, now physically, see, quantum mechanically, they are in this state. Okay, I am not allowed or I am not able to separate them as two quantum systems like this. I can't separate them because they become entangled. So this is a product state. Product state implies no entanglement. Okay, and quantum mechanically separable. Quantum mechanically. Okay, don't confuse with the classical, like a physical separable. Physical separable has nothing to do with quantum mechanically separable. Okay, so like a physical separation, let's say a couple is there, they are married, right? They work at different places, but they're still husband and wife. Their relation still exists. So they are like in relation, but physically they are separable like that. A and B is quantum mechanically not separable, but physically they can be separable. It's like two atoms put together in a box, made to interact and become two individual atoms and physically separable. We can have one atom in one box, another atom in other box. Okay. Now, if you just take atom A and take into your place, atom B into send it to some other place. Now they are in the entangled state like what I showed you here. Now, if you make a measurement on system A only, what we know, just now we saw, when you make a measurement, one of the state is going to come up, other going to be suppressed. Okay. Now, the quantum mechanical overall state is like this. Okay. Overall state is like this. I am writing explicitly the same thing here. Okay. Now, as we know, let's say system A, if A falls to zero state, which implies the probability amplitude multiplied or associated, I would say associated with one ket is put to, okay, I would write neatly, put to, okay, put to 0. So this one is going to be nullified. Now the problem is that is also multiplying 1 by square root of 2, also multiplying with the systems B 1 ket. So the system B's 1 ket is also destroyed. Okay. So overall state get destroyed, which implies, okay, both A and B are false, both are falling into 0 state. Okay, I've not done anything with the system B, but still it is falling into 0 state, which is, by the way, therefore, which is the entanglement implication. Okay, remember that. So it's very, very important. So this is only happening, I'm not saying only happens in the entanglement case. It happens in any case. Okay, right? So the number one fact we should know is observation of a quantum system leads to destruction of the quantumness. One of the implication is entanglement, enforcing without any communication between two parties the change in the fate of the system. Okay, right? So even though they're physically separable, physically separated, system A and B, something you do observation with system A also changes the system B. That is the amazing thing. Okay, right? So that is one. And number two is, as we have discussed already, cloning is not possible. No cloning. Okay, no cloning, or which comes with the no cloning theorem. Cloning is not possible in quantum computing. Okay, number two fact, right? So number two fact is that, and you can create the entanglement using multiple qubit gates. Okay, C naught gate and Hadamard gate, and so that is one thing. Okay, so these are the two facts which we are actually should know before getting into the quantum algorithms. Now, we have discussed on the way. If we come across some other facts, we'll list it out now continuously. I'll be sharing my hand notes to you people. Also, I'll be sharing my lecture notes, which is handwritten for your reference later. Okay, fine. So right now, let's go to some quantum algorithms. Okay, right? So quantum algorithms means what? You are going to execute a task with system of commands, which much more faster way, we are going to do, because we are already having a classical systems. We are happy with that. But why do we want to go to quantum systems or quantum algorithms? Because we want more. Okay. So what is that more is? See, there is something called quantum parallelism. Okay. What is quantum parallelism is? It's a parallel task. Okay. As we know, let's say there is a function f of x. Okay. There is a x values which will go into the function. Let's say it starts from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say there are 10 values. I have to calculate what is f of x. Let's say take example, f of x is equal to x square. It's a parabolic function. Okay. Now I have to feed x value and find out what is its functional form. So I would find 0, 1, 4, 9, 16, 25, 36, 49, 64, 81. Like that I calculated. Now if I ask the system to calculate, it just does that one by one. So let's say one by one it is doing. I want to accelerate the process. What I will do, I can divide the entire thing into parts. Let's say I have two processors. What I'll do, I'll divide the entire thing into two halves, and I'll ensure that calculation of each iteration is not depending on another iteration. So that means I can divide the entire domain into two parts. So there is a CPU1 does the top calculation, CPU2 does the bottom calculation. It's a two processors, okay, classical processing units, 1 and 2, accelerates two CPUs, accelerate, okay, accelerate not accelerates, it's accelerate the computation, okay, with the parallel computing that we know. Very good. Let's say somebody has 4 CPUs. What he can do? He can divide into 4 parts. Number 1, number 2, number 3, number 4, like that. So 4 parts you can divide. So further accelerate you can do. Further acceleration is possible. Okay. Provided each calculation doesn't depend on the other calculation. Now if you see, if such a thing is possible, then I can accelerate. Okay. Now, even such things are possible in classical computing, why are we going with a quantum computing? Okay. Now, why are we going quantum computing? We want more speed, more computation. Okay, I only gave a simple example here, but in fact, simple example, whatever I've given, okay, so there are so many complicated tasks. So in that complicated task, the time would require for each computation, each iteration, I want to reduce that. So we just look for, is there a quantum computing? The question is there a quantum computing method which could accelerate further? Okay, answer is yes. What is that? Is quantum parallelism. What is this quantum parallelism is? Okay, it takes all the x values in one shot. Okay, so quantum parallelism takes all x values in one shot and finds the f of x in one shot. Very important. Takes the values in one shot, calculates values in one shot. Probably, since it is a probabilistic nature, all the calculation, you might need to run each iteration several times to find the answer. But for sure, all the x values are taken in one shot and fed to the system, and the system would give you what is the functional value in one shot. Okay, so that is that very commendable thing, right? So we'll try to understand. Okay, let's understand this quantum parallelism. Okay, right? I'll write sometimes in a short form, not write full word. Okay, so what is that, by the way? Right? So to start with, let's say I have 2 numbers. What are the 2 numbers? Let's say x is 0 and 1. Okay, x is 0 and 1, and I want to find f of x for these values. Okay, that is what I want to do. I'll just start with the simple scenario, and then we will expand for more and more number of argument values, more number of x values. Okay, now as you can see, we have controlled NOT gate. Okay, let's take control NOT gate. Okay, I would say consider C0 gate. What it does, as you know, if there is a control, if there is a target, Control goes as it is without being manipulated or without being changed, but targets gets flipped by some value. Which value it is? Flipped. If x is equal to 0, nothing flips. If x is equal to 1, it flips. I can show you that example here. Let's say x is 0. Okay. If y is 1, x goes as it is. Even y goes as it is, because you add anything to 0, you are going to get anything itself. Okay. That is one situation. Another situation is, let's say x is equal to 1. In that case, if you see, okay, as you see, control goes as it is, target gets flipped up, okay, target gets flipped up. 1 to 1, you are going to get a 0. 1 plus 1 addition modulo is 2. 2 addition modulo with a 2 base is 0. So, you are going to get 0. So, the flipping taken place, flipping of target leads to this. No flipping in the previous case. Okay. So, that means the control makes a lot of command. Like it is tells whether to flip the target or not. Okay. So, as of now, we got that. Okay. Right. So, we got that. Now, in a short notation or a generic notation, I wrote this. Okay. What I wrote is, if the control is 0, the target would be gets added up by the control value with addition modulo. Okay. Now, in quantum computing, there is a possibility, okay, to have a quantum gate. I would say there is a possibility to have a quantum gate, okay, which not just adds x value to target, but it adds f of x value to target. Okay, I'll tell you what I mean. Okay, let me take it down this little bit. Okay, what I mean is, there exists a quantum gate which takes x value, takes target y value, it sends x as it is, but it sends y value as a y plus f of x. Okay, it's interesting. So what would be the output? Y plus f of x. Okay, quantum state. Not just x, we were adding x earlier. You see, we were adding x earlier. Now we are adding f of x earlier. So it's called a unitary functional gate, UF. Okay. Now you can ask a question: who would prepare? It's a matter of somebody, some experimentalist or some manufacturer who prepares for me this oracle or this black box for me, which takes two inputs x and y. The second input is added with the functional value of the first input. Okay, the possibility is there. Now if you carefully see, what happens if I send x is equal to 0? If I send x is equal to 0, 0 comes out as it is, and y equal to 1, if I send, for example, or let's take y is equal to also 0. Okay, what I'll get? 0 plus f of 0 I'll get. Okay, which is just simply f of 0, because you are adding anything to f of anything to 0, I'll get anything only. Okay, for anything if you add 0, I'll get anything only. So now if you see, from somewhere I got a function of f of 0 value. Beautiful, right? Now you leave the control as it is, sorry, target as it is. This time you give control as 1 cat, target is similar 0. So control goes as it is. Now target is 0 plus f of 1 you would get, which is f of 1 cat. Right? Now I have a privilege for understanding, analyzing the output at the target, okay, by analyzing the output at the target. By analyzing, I can find the function values f of 0 and f of 1. Okay, that is not the thing which I am expecting. I want to know both the functional values in one shot. Okay, right? I would say now the objective is to find both functional values, that is f of 0, f of 1 in one shot. That was the objective. Here I am just finding only individual values in f of 0 and f of 1. Is there a possibility? Answer is yes. How do I do that? I am just going to do that by, okay, I am going to do that by introducing superposition state. Instead of sending single state, I will be introducing superposition state this time. How do I do? I take the same neutral function, okay, I'll keep the target with a 0, okay, and I will keep the control as a superposition of 0 plus 1 divided by square root of 2. Okay, as you guys know, Hadamard does that for us. Okay, okay, what Hadamard does, just take a 0 cat, send through a Hadamard gate, you would get superposition of 0 plus 1 divided by square root of 2. Okay, classical bit converted to quantum bit, it's a qubit, superposition state. Okay, so that is something very good which I was expecting, which is I want. Okay, now if you say C, okay, what happens if I send a superposition to control? Target is left as it is. Now in quantum computing, things will go through the gate just like railway boxes going through certain station or certain points. Okay, so what you do at this point, what is the quantum state? Let's list it out. So 0 cat plus 1 cat divided by square root of 2, tensor product of 0. This is the parallel processing. So the control is on the left, target is on the right. Okay, very good. Now you can write this explicitly by multiplying tensor way 0 tensor 0 plus 1 tensor 0 divided by square root of 2 square root of 2. Explicitly I am writing. Remember, there are short ways. Short ways means shorthand notations. A tensor product between x to y is also written as xy10. like that. Okay, right? So that is what we can write in short form also. 0 0 plus 1 0 divided by square root of 2. People write that in short form. Okay, shorthand notation. Okay, fine. So, right now, if you just to see, now control is some value, target is some value. What happens through the C naught gate? So the C naught gate operation which we had, so control is 0, target doesn't change. Control is 1, target should flip. But I have a unitary functional gate just like a C naught gate. It adds the functional form to the control. So I have my input state in like this. Now I want to know what is the output state, which is unitary function acting on the sign, which is unitary acting on 0 0 plus unitary acting on 1 0 divided by square root of 2. Okay, as we already know. Okay, wait a minute. As we already know, unitary acting on the with the control 0, target gets added up with the functional value of control. Very good. If you want, you can put a comma just for your convenience. Okay, and I'll also put a comma for the later case where the target is anyway 0. For that, you are adding f of 1 divided by square root of 2. Now, if you carefully see here, you are adding 0 to f of 0, 0 to f of 1. So they are not going to change anyway. I'll have psi out is equal to 0 comma f of 0 plus 1 comma f of 1. Okay, divided by square root of 2. If you want, you can show them as 0 f of 0 cat 1 f of 1 cat divided by square root of 2. Now, looking at the output state, I see the information of f of 0, information of f of 1 in it. Okay. So, by analyzing psi out, okay, psi outs you can say second register, quantum register. The first register is this one. The first registers are this one, and second registers are this one. Okay, by analyzing psi out's second register, we could find f of 0 and f of 1 in one shot. Beautiful, right? Very important. So if you are able to find in one shot, boom, you can able to find two values of function in one shot. Now let's improvise or upgrade. What I am going to upgrade is, okay, I'm not satisfied with just two values. I want to do it for four values. Let's say x is, okay, let's say I have x values 0, 1, 2, 3. Four values are there. What I will do, the binary conversion, binary x should be, okay, 0, 0, 0, 1, 1, 0, 1, 1. That is the binary version of 0, 1, 2, 3, four numbers. Okay. Now I want to find what is the f of x. I want to find. As we see, there are four values of x argument. I want to find functional values of this particular argument values. Earlier, I was feeding a superposition state as a control. Here you see superposition state as a control, which is allowing me to give two functional values in one shot as, okay, as this way. Okay. Now the question is, I want to have four values, four functional values at a time. The only trick we will be doing is, since to feed the four numbers, we need what? We would be needing two qubits. Okay. As we know, one qubit stores two numbers, two qubit. Okay, two qubit would store four numbers. 2 to the power of n is equal to 2 is 4. So you take 2 qubits, which gives me 4 memory locations, which stores all the x values, which capable of taking all 4 x values. Okay. Now, quantum mechanically, how do I create these 4 possible memories is, okay, how do I store 4 possible memories is, okay, so you just take 0 ket 1 Hadamard, giving me two superpositions, sorry, one superposition. Okay, what I'll do, I'll take one more qubit in the ground initially, and I'll send it through another Hadamard. Okay, so I'll have one more superposition. Let's take what is the states going through this couple of Hadamards. Okay, so on the left hand side I have 0, 0 going through two Hadamards. I'll write as a tensor square. Okay, going to give me 0 plus 1 ket divided by square root of 2 tensor 0 ket plus 1 ket divided by square root of 2 another tensor. Okay, so what you see here, okay, let me write down explicitly. This is 0 ket 0 ket 0 ket 1 ket 1 ket 0 ket plus 1 ket 1 ket divided by 2. See, there are 2 square root of 2. Square root of 2 is there. Multiplied, I'll get 2. So I created an equal superposition, higher dimensional quantum system like we saw earlier, with the two quantum systems put together. So two quantum system in the superposition. Remember, very, very important, superpositions. Okay. So when I put two superpositions together, I am going to generate new bases. Okay. Like this. New basis is created of 4 dimension. Okay. That means I am having a chance to feed 4 values to my unitary functional gate. Okay. Now you will take a unitary functional gate, unitary functional. This time in the query part or a control part, they call it a query part also. I'll have 2 Hadamards. Starting with the 0, 0 here. At this point, I'll have this superposition state, this superposition state, what I was referring earlier, 0, 0, 0, 1 plus 1, 0 plus 1, 1 divided by 2. In the control part, target part, I'll have 0 only. Okay. So if you do that, I would be getting some control output. I am not bothered what is the control output. What I am bothered more, what comes at the target. That is the information which carries, right? So what happens at the target, okay? So that is what more important for me. So at this point, if you just see, I'll have something. Now, as we know, let me list down what is the sign in the first place. At this point, sign is there. Okay, if you want the sign not, you can write first. Okay, what I mean is at this point I have a sign out, which is tensor product between two query registers and one target. So this is query part we call query or control register or registers. This is target register. Okay, quantum register. Now these things going in, okay, and one Hadamard on the control, another Hadamard on the control, nothing on identity I'll put for the target. So which is going to give me sign. Okay, so sign is okay superposition of 0, 0, 1, 1, 0, 1, 1 divided by 2 tensor product with the 0 ket. That is what the sign is. Okay, now I want to find out what is the unitary effect on the sign. Okay, which is going to give me psi out. Okay, so the psi out, if you carefully write down, just to take the inference from the previous case. What is the previous case? Okay, whenever the control is something is there, that control value in the functional form gets added up for the target. You see, so which means I can just do the same analogy. Okay, so let's explicitly write down. Okay, so here I have control is 0, 0. Okay, so what is the target? Target is 0 plus f of 0, 0. That is one entry. Whenever is control is 0, 1. Okay, target is added up with the functional 0, 1 plus whenever is control is 1, 0, target is added with the 1, 0 plus whenever is control is 1, 1, target is added with the 1, 1. This entire thing divided by 1 by 2. Okay, so I have not done anything. So target is 0. For every case, I am adding the functional form of the control value. Okay, so now you see, you are adding 0 to all these functional values. You are not going to change anything. So you can write down the output as 0, 0, f of 0, 0 plus 0, 1, f of 0, 1 in the ket form. F of 1, 0, f of 1, 0 plus 1, 1, f of 1, 1 divided by 2. So that is what your psi out. Now, by analyzing, okay, analyzing psi out, we can find, okay, f of 0, 0 value, f of 1, 0 value, f of 0, 1 value, and f of 1 value in one shot. That is what? The quantum parallelism is allowing me to find 4 functional values in one shot. Okay, so now let's generalize. Okay, do we have a space for generalization? Yes, let's generalize. Okay, what I mean is I want to find n. Okay, generalize. If I wanted to find, or if you want, let's say, before generalizing, let's generalize to 8 values. 8 values of x. Okay, so I want to find, okay, 8 values of, okay, find f of x for 8 values of x. What I will do, I will taking, instead of taking just 2 control parts, I will take a 3 control with 3 hadamarts. Okay, right? So 3 hadamarts I will take, all of them in zeros. Target is also in 0. So I will be getting, what I will be getting? I will be able to find, okay, able to find what are the 8 possible situations. Now at this point, what is the situation? This is the control register. What you will have? I'll have 0, 0, 0, 0, 0, 1 plus 0, 1, 0, 1, 0, 0 plus 1, 0, 1 plus 1, 1, 0 plus 0, 1, 1 plus 1, 1, 1 divided by square root of 2 to the power of 3. Remember, so earlier it is square root of 2 to the power of 2, which is actually 2. Here in this case, square root of 8 is the probability amplitude. Okay, 1 by square root of 8. So this is the query part. Okay, so the query part takes the 8 possible values through it and feeds to the unitary function, and you would be able to find f of 0, 0, 0, f of 0, 0, 1, f of 0, 1, 0, f of 1, 0, 0, okay, and f of 1, 0, 1, f of 1, 1, 0, f of 0, 1, 1, okay, and f of 1, 1, 1. So you're able to find all 8 values of f of x by analyzing. So this is generalization for a 3 system. Sorry, a generalization for 8 values. Now, let's say I have generalization to any n. So, okay, any n values of x. I want to generalize. So what I will do, let's say there is n is very large. So I will choose small n number of qubits such a way I will cover all the n values. Okay, where n is the number of qubits needed, number of qubits required to store all n values. Okay, so if all n values are 8, 3 qubits are required. All n values are 16, 4 qubits are required. Okay, so in this case, what I will be having? I'll having very large unitary gate where, okay, where there is several hadamarts acting on several zeros. I will write this time in short as input states are in n tensor. Okay, remember input states n tensor mean 0, tensor 0 and so on up to n times. Okay, similarly that is acted with the hadamard n times. So hadamard n times mean hadamard, hadamard and so on, hadamard n times. Okay, so that feeds as a control part of unitary function, and target is just a 0, and I'll have, okay, so if you want you can just broaden or thicken that line so that it is not any regular single qubit register, it's a combination of many registers. Okay, and I will have this time finding, this time I am able to find, okay, I am able to find how many values? Functional f of 0, 0, 0 n times, comma f of 0, 0, 0, 0 1. Yeah, okay. So here remember there is a zeros n minus 1 times, and there is 1 here. Okay. So likewise, I am able to find 1, 1, 1 n times. Okay. So overall 2 to the power of n, which is n capital N functional values, we can find in one shot. Okay. So this is a very, very powerful thing. So this is a quantum parallelism for you. So the quantum computing or quantum circuits would allow you to find all the functional values in one shot. Okay. So that is very, very commendable. So in short, if you want to generalize in right, so what you do is your input is, okay, summation over n, summation over n, sorry, 2 to the power of n, not just n, summation over 2 to n, 1 by 2, probability amplitude is 1 by 2 to the power of n, summation over 2 to the power of n, x cat, okay, right, and 0 cat, this is the input, okay, where I'll just put over 2 to the power of n, right, x belongs to, okay, x belongs to 0 cat, 1 cat, tensor n. Okay, how many such values will be there? 2 to the power of n values are there. So this is what goes through quantum gate of unitary. Now, unitary action on psi in gives you psi out. Okay. Now, if you want to write down what is the psi out would look like, which is going to be, okay, 1 over 2 to the power of n. Remember, 1 over 2 to the power of n this time belongs to, x belongs to 0, 1 tends to the power of n, x cat, f of x cat. Okay, right? If you put n equal to 1, we'll get back the old situation. What is the output? Output is x f of x divided by 1 over 2, which is x is 0. So x belongs to 0, 1, right? So x is 0, f of 0. X is 1, f of 1. So you would find that divided by.
Sorry to disturb you.
Yeah, ma'am. I'll give the gap. Yes.
Okay.
Okay, right. So just a minute. I'll conclude and give the gap here. Okay. Fine. So with this, you can also give it for n equal to 2 case. You will get the previous whatever we discussed. So this is what the quantum parallelism for you. We can use this and we can get multiple effects or many more like advantages in quantum computing that we will see in the next part of the session. Okay, so we'll take a quick break. Now it is 11:12. We'll assemble back at 11:16. Sorry, 11:17. Thank you.
Participants quiz is posted in the chat box. Sir, could you give some idea about how to solve the quiz?
Oh, okay, okay, ma'am. Okay, let me see if there are any questions. Uh, all right. The questions. Okay, I don't see like questions which I have given. I think.
Sir, actually, we have posted some different questions. Actually, yesterday we have posted 10 questions, so that today we have posted some different questions.
Oh, I don't
So
see those
kindly
questions,
see that.
madam. If I see the questions, I can. Okay, this is a quiz one form, is it? Okay, let me see. Ah, okay, okay, okay. Yeah, yeah. Okay, so yeah, I'll just. Okay, okay. Alice and Bob provided with the binary strings, and Alice has determined a Boolean function with least communication between herself and Bob. Consider the parity function where plus is a XOR operation. Bob communicates a bit string W to Alice so that she can determine F. Okay, what is the minimum number of bits that can represent W? Okay, this is just like Dutch algorithm and Dutch Joyce algorithm. We'll discuss this today, and probably you can answer that after that. Okay, and consider 2 by 2 matrix. Second question I'm just looking at. Okay, where x2, I2, and 0, 2 are given. Which are of the following? Okay, let me. Okay, so I need to share the screen, right? Okay, wait a minute. It is there in the chat messages, right? Okay. So maybe chat messages. Maybe I can share my other screen so that you people can see quickly. Yeah. Okay. Right. So this is what I see. Which of the following 4 by 4 matrix represents a unitary function UF that implements the function f of x, which is equal to negation of x. Okay. So there's a small correction. It is not 4 by 4 matrix. It's 2 by 2 matrix. Okay. So, oh, okay. It's a 4 by 4 matrix only. Unitary f. This is what we have discussed. Okay. Which one does that? Right. Unitary function. Unitary function. Okay. So, the unitary function which we just defined so far. Okay. So one of them actually falls into this form. I think I'll discuss this again. So only two questions are there. Yeah, I think only two questions. Yeah, I think I'll discuss this in detail. Yeah. Yes, everyone, I think welcome back. We can start. Okay. So, madam asked me to discuss about the problems, how to solve them. A couple of them I think I see. Okay. So, uh, once you submit, I think, okay, there are only two questions. Okay. Right. One and two. Uh, I'll try to clarify, give you some idea so that you will get. Okay. So, as you can see, let's say just take a CNOT gate. Okay. So I'll say quiz one discussion. I think this is quiz one, I guess. Okay. Just take CNOT. Just take a CNOT gate. Okay. What it does, it takes control either in 0 or 1 form and gives you the output as it is. Okay. If the control is 0, nothing happens to the target. If the control is 1, okay, right? So target gets added up with the control value, which is actually flipped version. Now, if you see in the left hand side what is going in, on the right hand side after the C naught, what is comes out, you can put it into a box of quantum gate if you want. Okay. So the input is 0, 0 and 0, 1, sorry, 1, 0. Okay. 1, 0. So what is 0, 0? 0, 0 is 0 tensor 0, which is 1, 0, 1, 0. This is going to give you, take this multiplied to both of them. Take this multiplied to both of them. So what you will get? You will get 1 followed by 3 zeros. Okay? Right? Similarly, you can find for 1, 0, what is the column representation, which is about 4 by 1 dimension. Now, here you see, in the last case, where control is 1, target is being flipped, okay, where what is the output? Output is 1, 1. Okay, see, control is 1, target is 1. So what is the tensor product? 1 tensor 1, which is 0, 1 tensor 0, 1. If you carefully find out what it is 3 zeros followed by 1. Okay. Now the question is, what is the transformation matrix? What is the unitary matrix? I'll not say X, unitary F. I'll say unitary sum transformation gate, which acts on 1, 0, gives you 1, 1. That is the question. Now, what is this? Okay, that was the question asked to you, right? Unitary functional gate, which does one change from 1, 0 to 1, 1. Now, as you see, this is about 4 by 1 dimension. This is about 4 by 1 dimension. So obviously U2 has to be 4 by 4 dimension. Okay. Now if you see 4 by 4 means I'll have 4 by 4 number of elements in it. I don't see any effect on the control. Control goes as it is. You can simply put a first quadrant 1, 0, 0, 1. Identity. Okay. Right. And so the target is being flipped. Flipping happens with the X gate. So the X gate, you can put the fourth quadrant You can leave everything else as is, zeros. By trial and error method, you can find the unitary transformation gate which acts on zero, flips the target. So this is in fact equivalent to identity 0, 0 and identity. So this is the 4 by 4 matrix which was asked in the quiz. Okay. So I'll tell you, please cross check before answering. I may be wrong. I may be right. We don't know. So you should check whether this unitary gate which is going to give me the certain above change. What is one more? UT acting on 1 1 should give me 1 0. So you should check. If yes, you can answer as per the above. Okay, right? That's the hint I am giving for your second question. For the first question, it is about Dutch algorithm and Dutch Joyce algorithm. We are going to discuss that now. Okay. So after going through this Dutch Joyce algorithm, you would be able to understand that first question and you would be able to answer. Okay. So let's conclude wherever we stop. Wherever we stopped is we can able to find the multiple function values in one shot by taking quantum parallelism circuit. What is a quantum parallelism circuit? It will adapt as per my requirement and gives you that required functional form and a study in one shot. Okay. Now, as we have done that, now let's go for little bit more. What is that little bit more is? Okay. We will going to do the Dutch algorithm. So the Dutch algorithm is, okay, let's go to the Dutch algorithm. Okay, so DUESCH algorithm. What this algorithm does is it takes the quantum parallelism, it takes that, and it adds another feature which is called quantum interference. Okay, and gives the okay gives the ability to find the sum of functional values. Okay, so that is what the Dutch algorithm is. Not just only functional values, not just f of 0, f of 1, f of 2, f of 3. We'll also able to find the sum of functional values. That is the Dutch algorithm. Okay. Now, before going there, let's first understand what is quantum interference. Okay. Let's understand what is quantum interference. Okay. Let's understand. So the moment I say interference, probably the engineering people might have gone through their 11th and 12th standard, the Young's double slit experiment. Okay, even for 11th and 12th it is there. Okay, even in degree it is there. Engineering it is there. What is that? You just take a laser light or coherent light. Okay, light comes through and you put a two slit. Okay, okay, let me draw it little bit. Okay, one. Now there is a slit 1, there is a slit 2. Now the light from here goes through, let's say it is diverging, let's say it's diverging. The light goes through this slit, and that light of the slit S1 acts like its own source, slit S2 acts like its own source, like two lasers, individual lasers. Now there is a screen at this point. Okay. Now light usually travels in the waveform, like a sinusoidal wave, going through like up and down. So let's take one point on the screen. Let's say light travels like this and hits that the point with the wave from the bottom, like a signal from the bottom. Let's say from another source, light goes through and hits from the top. Okay. Now you see the light is interacting here in opposite way. Let's say the phase with the light is one is from the top, it is coming down. From the bottom, like another wave is coming from the bottom. It's like if the strength of the wave is there, both the waves are trying to pull something towards that, or try to push in equal force. So what happens? Two people are trying to pull something towards each other. Their equal strength, they will not move at all because they can't. They are of equal strength. So the light interferes. The wave of light interferes. One part of the wave interferes from the top. Another wave coming from another source interferes from the bottom. They actually destructively interfere. They create a dark fringe, darkness there. Even though two light rays comes and interact, they should amplify because they're interfering destructively. So destructive interference, okay, creates a dark fringe. Okay, so I will say darkness. Right? Now the dark fringe is created. There are locations where light goes and hits in a positive way. Okay, right? So there is a constructive interference. Okay, so there is a bright fringe. So that is what interference fringes actually created when I have a double slit experiment where if you see there is a bright fringe, dark fringe, bright fringe, dark fringe, bright fringe, dark fringe. So the intensity of light is shown here. So the bright fringe is there. Okay, intensity of light. Okay, so this is what quantum interference. Why is so quantum is light is consisting of particles. Particles are photons. They're quantum in nature. Those are like travels like a waves. They go and interact at different points, whether it's constructively or destructively. Whenever there is a constructive interference, the light amplifies. Whenever there is a destructive interference, light is going to nullify the intensity. Okay. Now that is the quantum interference. What is that has to do with quantum algorithm, Dutch algorithm? We just take the idea of constructive and destructive interference here. So here the quantum interference mean in Dutch algorithm is you are going to find the functional sum. So on to n. So I'm putting x values as it is. If I want in a binary form, okay, f of 0, 0, 0, f of 0, 0, 0, 1, f of 0, 0, 0, 1, 0, okay, f of 1, 1 up to n. Okay, so this is what you are going to find along with finding a function value. Let me write down a conclusion now. along with finding f of, okay, f of x functional values, you would also find, or you would be able to find, okay, the sum of various f of x values in one shot. Remember, again, that is in one shot. Okay. So if somebody tells you, you are not only going to find a function value, you are also going to find multiple function values plus their sum. It's a bonus for you. Okay. So that is what the Dutch algorithm is. A Dutch algorithm. Now the question is how? How to do? How to do that? Right? So what we do, we can fiddle little bit with whatever parallelism circuit we have. Okay, that is by, answer is by adopting the quantum parallelism circuit for the Dutch algorithm. What is the adoption? Okay, for simple case we'll just take, for one of the case we'll just take, what is that one of the case? Let's say I have two values. Okay, I have two values. I want to find the sum of the function values. Okay, and I want to find the sum of the function values and also the individual function values and also sum of the function values I want to find. Okay, so that is what I want to do. Okay, wait a minute. Let me put it cross check my circuit. Yeah. So what exactly we are going to adopt is, we'll just take the same circuit, unitary function. As we know, it takes x, takes y, sends x as it is, but y is getting added up with f of x. We know that. And we will have a Hadamard gate here that we say, instead of just leaving the control, sorry, target as a single bit, what I will do, okay, we will have the target as one, and we will have one more Hadamard for the target, and we'll send through, and we'll have Hadamard at the control to put back the state into the old form. It is started with a 0. Okay, so this is what Dutch algorithm circuit would look like. Okay, so the only difference from previous case to this case is I added an extra Hadamard for the target. I flipped the target from 0 to 1. Okay, and I added one Hadamard at the control after the unitary function. So this is the difference between previous case to this case. Now let's try to understand what happens if I have a circuit like this. Okay, so usual way of dealing with the quantum circuits is divide the circuit into parts, layers. Okay, and in each layer, what is the state of the quantum system? If you find out, it is easier. Now, if you see at a very initial stage, I have, let's say, psi naught. After a couple of Hadamards, it becomes psi 1. After a unitary gate, it becomes psi 2. After one Hadamard gate at the control, it becomes psi 3. Okay, so this is what I have. Now let me find out what is the psi naught. Psi naught is 0 tensor 1. This is the initial state. Okay, what is a psi 1 by the way? Psi 1 is One Hadamard act on the control, one Hadamard act on the target, which is a superposition of control with a positive parity divided by square root of 2, and another one is superposition with a negative parity between 0 and 1. This is what I have. Okay, right? Now, unitary function acts on psi 1. This is going to give you psi 2. I want to find out that. How to find? Okay, but the thing is, I see my x is in superposition, y is in superposition. Okay, so there is a trick I want to find. There is easiest way to find what happens when x is in superposition onto y, which is also in superposition. Okay, so what I'll do now, okay, what I'll do now is I'll just take x is control is in some generic form, okay, and target is 0 minus 1 divided by square root of 2. This is what I say. Let's consider now unitary action on this situation. Okay, why do I want to know where x could be 0 or 1? Okay, so in that case I want to find out. Now as you see, unitary acting on such system is going to give you control as it is, target being flipped with the functional value of x. Okay, let me write down that neatly again to just avoid any confusion. Minus, okay, let me write down the x also inside so that you will not get confused. Okay, x cat and x cat 1 plus f of x. This is what the unitary acting on the input state like this. Okay, now let's just try to simplify. You add a 0 to any function, it becomes any function. Okay, right? You add 1 to any function, we don't know what is f of x, by the way, so I'll keep it as it is, 1 plus f of x divided by square root of 2. Okay, now if you carefully look at this output, if you want, you can just write down in a short notation, which is x output, okay, f of x minus 1 plus f of x divided by square root of 2. This is the state I have. Now if you look at carefully f of x values, okay, you look at f of x values, and according to f of x values, you can generalize or simplify this equation. What is that is, see, f of x would take 0 or 1 values. Okay, that we know. In binary system, the function values cannot be 0 or 1. That's all. Okay, so when f of x is equal to 0 implies what? The output is x 0 cat 0 plus 1 is 1 cat divided by square root of 2. Okay, when f of x is equal to 1 implies x into, I'm writing this, okay, 1 cat minus 1 plus 1 is 0, so the 0 cat divided by square root of 2. Now if you carefully see, when f of x is equal to 0, I am getting the system. When f of x is equal to 1, I will get a minus of x 0 cat minus 1 divided by square root of 2. So in both the case I am getting the same function, but the second case I am getting minus 1. So I can generalize or simplify this in a very handy notation, like I'll just write a handy notation, which is equal to minus 1 to the power of f of x cat 0 minus 1 divided by square root of 2. So this is a unitary functional gate acting on some arbitrary control with a target in a negative negative superposition. So parity 0 minus 1 is a negative parity superposition I'm calling. Okay. So this I have. Very good. Okay. Next, right. Next, I can also assess this input and output based on x in a generic form. Okay, as we know, x is when x is equal to 0. Cat, what happens? So let me write down when x is equal to 0. Okay, what I'll have on the left is unitary acting on 0, 0 minus 1 divided by square root of 2 is equal to minus 1 to the power of, remember, I'm not allowed to change the function value, but I'm allowed to change the x value. So this is f of 0, 0 cat, 0 minus 1 divided by square root of 2. What I did, just according to x value, I just replaced the above function with x value. Now, unitary acting on when x is equal to 1. Okay, right? When x is equal to 1, I'll have 0 minus 1 minus 1 to the power of f of 1, 1 cat, 0 minus 1, 0. Okay, so when I found the generic case of f of x case, generic case of x case, so now what I'll do, I can sum both the equations, above equation, let me call 1 and 2. Sum the above two equations and divided by square root of 2, I will have what is the effect of, okay, what is the effect of control going with the superposition, target is in the superposition. Okay, so that was my actual objective. Actual objective is unitary acting on psi 1 giving psi 2, right? So how is that I'm trying to find it. Okay, so now let's add equation 1 and 2 and divided by square root of 2. What I'll have is unitary function acting on 0 plus 1 divided by square root of 2. What I mean is, okay, 0 minus 1 divided by square root of 2 is going to give you minus 1 to the power of f of 0, okay, 0 cat, plus minus 1 to the power of f of 1 cat divided by square root of 2, and the right hand side the target remains the same. Okay, so this is what I get from adding 1 plus 2 divided by square root of 2. Equation 1 and 2. Right? So if you carefully see this, okay, if you carefully see this, unitary acting on function value, unitary function acting on positive superposition as a control, negative superposition as a target, giving you something. Okay. Now, as we know, the function values can take 0 and 1. Okay. So let's do some discussion. What is this discussion is? Okay. Let's say the various possibilities I'm talking about. Let's say function values both are equal to 0. Okay. So in that case, what happens? From the above, if you write down, so the output would be, wait a minute, unitary function acting on 0 plus 1 divided by square root of 2, 0 minus 1 divided by square root of 2 is going to be minus 1 to the power of f of 0, where f of 0 is 0. So I'll have 1 minus 1 divided by minus 1 to the power of 0 is just a plus 1. Okay, let me remove that and just put 1. Okay, so I'll have this output. Okay. Now, if you carefully see, f of 0 is equal to f of 1 is equal to 1. In that case, what is the input to the output? Okay, which is minus 1 to the power of 1 is minus 1. Okay, okay, just a minute. Minus 1, 0 cat. Minus 1 to the power of f of 1 is again minus 1. So minus 1, 1 cat divided by square root of 2, 0 minus 1 divided by square root of 2. Now I can take the common of minus outside and write down this as minus of 0 minus 0 plus 1 divided by square root of 2, 0 minus 1 divided by square root of 2. Okay? You see now? If you just compare previous case to this case, only difference is minus 1. Okay? So what I will do, I'll generalize, or I can just summarize this into one simple equation. What is that equation is? The output is equal to plus or minus 1, 0 minus. Okay. So whenever the plus will come when both the functional values are 0, minus will come both the functional values are 1. Okay. So what you do if f of 0 is equal to f of 1? So this is a situation. Okay. Now, not always f of 0 and f of 1 are same. They may be different. So we need to consider that also. What is that case is when f of 0 is 0, f of 1 is 1. So I am talking about f of 0 not equal to f of 1 case. Okay. In that case, what you see from the above, unitary, yeah, from here, this is our actual expression. From here, you can find out unitary acting on positive superposition with the negative superposition as a target. Okay, is going to give you, let's say minus 1 to the power of 0 is just 1, that is 0 cat. Minus 1 to the power of 1 is minus 1 divided by square root of 2, 0 minus 1 divided by square root of 2. You can cross check whatever I have written from this expression. Okay, right? From that expression I have written. Now, when f of 0 is 1, f of 1 is equal to 0. In that case, again you can write down okay, right? What you will get? Minus 0 cat plus 1 cat divided by square root of 2, 0 minus 1 divided by square root of 2. Now you can just take a minus common in the second expression. What you do? You can put minus outside. Okay. Now compare to just comparing first and second equation. You see this equation and this equation. I can generalize. What is the generalization is? Okay. Okay. Let me generalize. Unitary acting on positive superposition as a control, negative superposition as a target, going to give me plus or minus 1, 0 minus 0 minus 1, okay, where f of 0 not equal to f of 1. Okay, beautiful. I got all the 4 cases. One is the cases when f of functional values are both are equal. Another case is functional values are not equal. Each case would come up with 2 options. Okay, one is this, another one is this, one is this, another one is this. Okay, all the 4 options were covered. Now the question is, can we put all the 4 options into one expression? Okay, so let me put that in a in the boxes so that we will have a highlighting. Okay, one, okay, two, and like 2 boxes, last 2 boxes, we want to generalize. Of course, there is a possibility. What is that possibility is, okay, psi of 2 is equal to unitary function on psi of 1 is equal to plus or minus 0k plus 1k divided by square root of 2, 0 minus 1 divided by square root of 2, okay, plus or minus 0 minus 1 divided by square root of 2, 0 minus 1 divided by square root of 2 for f of 0 is equal to f of 1 for f of 0 not equal to f of 1. Okay, beautiful, right? So all the 4 cases were just summarized into 2 equations. Now question is, can I summarize this into one single equation? Okay, right? So that was the target. Now carefully, if we just see, in the above case, the functional values both can be 0, right? So function values both can be 0 means, okay, just a minute, both can be 0 means I will get a sum equal to 0. When function values both can be 1 means, again I will get function values, okay, for f of 0 is equal to f of 1. Okay, so when one of them is opposite to each other, so in that case I'll get 1 for f of 0 not equal to f of 1. As we see this relation, using this relation, am I allowed to generalize the above situation? Okay, so you keep this aside right now. Now let's get back and see what is the quantum circuit what we have in the Dutch algorithm. So in the Dutch algorithm, what it says, there is a Hadamard acting on the control on psi 2 gives you psi 3. Okay, so let's find out what is the psi 3. Okay, psi 2 I know. Okay, let me go to the next page. Psi 2 I know. This is a psi 2. Okay, so there is a positive superposition at the control, and there is a negative superposition at the control. Now let me find out what is psi 3. Psi 3 is Hadamard acting on the control, nothing is on the target. This is the psi 3. Okay, so now I have positive superposition at the control, negative superposition at the control, 2 cases. Now, so I'll have my psi 3 with 2 cases. What is that? Psi 3 is Hadamard acting on a positive superposition, nothing is on the target. Hadamard acting on the negative superposition, nothing is on the target. Okay, first case when f of 1 is equal to f of 0. The second case f of 1 is not equal to f of 1. Okay, so these are the situations. Now as we know, right, remember Hadamard action gives you a superposition state, that is 0 plus 1 divided by square root of 2. If you act Hadamard again, you are going to get back 0, right? Similarly, Hadamard acting on 1 gives you minus ket. Hadamard act on minus ket gives you 1 ket. So my psi 3 here is 0 ket, 0 plus minus 1 divided by square root of 2, 1 ket, 0 minus 1 divided by square root of 2, when f of is equal to f of 1, f of 0 not equal to f of 1. Okay, so my psi 3 I got. Now let's get back this situation. When both the functions are 0, the sum is 0. When both the functions are both the functions are not equal, their sum is 1. So what I see here is When both the functions are same, I'm getting 0. When both the functions are unequal, I'll getting 1. So is there any generalization I can do? Of course, yes, I can do. I'll just simply say, this is my output. Okay. What did I do with that? I captured both the situations with one simple equation. What is that? The sum is equal to the first case when both of them are equal. Sum is equal to 1 ket when both of them are unequal. Okay. So beautifully, I was able to get the sum of the function values in one shot. Remember, the plus or minus we should not ignore. This plus or minus, this plus or minus. Okay. Okay, I should not ignore here. Okay. So this is a Dutch algorithm for you. For two values, I can find the function values and their sum also, right? So how do I find function values? What I do, I just remove one of the Hadamard, okay, from the circuit and then get the individual function values. Whenever I need some values, some of them, I'll put the Hadamard also. Okay, now generalization to any function values. Okay, what I do now, let's say I want to find sum of the four functional values. Let's say, okay, right, we want to find f of 0, f of 1, f of 10, f of 11. Addition model. Remember, we want to find all the sum values. Okay, right? Generalization to any function values and their sum. Okay, so to find this, what we will do, instead of taking one Hadamard, we will take one more Hadamard. Okay, 0, 0, 1. Okay, here I'll have two Hadamards and takes out. Okay, so this would give me at the output side out is going to give me plus or minus all the functional sum. Okay, with the negative superposition. Okay, so this is what we will find through Dutch algorithm. Okay, right? So the extension of this is called a Dutch-Joyce algorithm, where we can find whether the used function is of what kind. Used function is of what kind is. So I'll take 5 more minutes. Since we started little bit 5 minutes late, so I'll take 5 more minutes. Okay. So Dutch-Joyce algorithm is, okay, extension of this. What is that is, let's say I have a function which takes x values, gives you 0 for all x or 1 for all x. So this function is called constant function. Okay, right? And sometimes it gives you 0 for half the set of x values and 1 for another half. Okay, so this is called a balanced function. So on the above, the function, if it starts with 0 value, it remains 0, or starts with 1 value, it remains 1. In the bottom, what I have is If it is for half values, it gives you 0. For other half values, it gives you 1. Now the question is how to find f of x is constant or balanced by checking least number of attempts and least number of calculations. Okay, right? So in general, what I would be needing is, okay, so I would be needing x values. I'll feed x values 0, 1, 2, 3, and so on, and find out what is f of x. Let's say I have 9 values. Let's say 9, 3, 4, 5, okay, 6, 7, 8, 9, 10 values. Okay, so for the first input, it gives you 0. Second input, 0, 0, 0. For the 4 values, it is given 0. So I don't know still, it is a 0 or 1. So again, it gives you 0. Okay, means I can still don't know. If the next one is 1, the fifth entry means, sorry, if the sixth entry is 1, means I can simply ignore and not calculating remaining values. You can put that because, okay, for the half of values, it is already given 0. For the remaining half value, if it is the next value is 1, the function is balanced. Okay, otherwise, let's say, right, if the function next value is 0, no need to calculate, no need to find for remaining values. Okay, so what I mean, if sixth entry is 0, you can simply say 0, 0, 0, 0. So this is a constant function. Okay, so one of the question in your quiz is, how many number of attempts are required to find whether the function is balanced or not, or it is a game between Alice and Bob. Let's say Bob uses this some function. Alice wants to find whether the function is balanced or not. How she finds? She sends the x value to Bob. Bob calculates f of x value, sends back to Alice in each iteration. Let's say it's Alice and Bob. Okay, Bob has f of x. Alice gives you x value. Bob calculates f of x value, gives back, and Alice analyzes this f of x value and finds and notes down that f of x value here. And so one complete iteration is sending a value and get back the function value. Okay, so on any given day, Alice requires, if the size of the data size is n, so she would be needing n by 2 plus 1 iterations or attempts or iterations to find the function is balanced or constant. Okay, that many attempts are required for Alice. So on the worst day, she would be needing this. But on the good day, let's say in 2 attempts she can find, because first one she got 0. So for example, for f of x is equal to 0, she got 0. F of x is equal to 1, she got 1. Okay, amazing. She got in 2 attempts, so the function is actually balanced. No need to go for the remaining calculations. With 2 iterations, balanced found with 2 attempts. But not every day this happens. Now this is a lucky day for us. Okay, so classical computation requires this n by 2 plus 1 attempts if n is the size of x set. Okay, right? So if you use Dutch Joyce algorithm, okay, if you use, then you can find you can find f of x is balanced or not in one shot or one iteration. Very, very important. Okay. So how it is done is she feeds all the n values into the quantum system. Okay. She fits all the values into the quantum system, makes a quantum gate, sorry, quantum superposition, feeds uh, all of them into the unitary function value gate. Okay, and she could easily find the answer whether the function is balanced or not simply by doing analysis with the output state. Okay, so that is a Dutch Joyce algorithm for you. It takes much more time to explain that. So I would be sharing my hand notes, lecture notes for you. You whatever we did for Dutch algorithm, if you follow through, you definitely understand. Okay, so the proof is in the lecture notes. Please refer. Okay. So I'll just stop at this point. We are already 10 minutes overboard. So not to waste others' time. Okay. So I'll be sharing this notes, whatever I presented with my blackboard writing, and also my hand notes to you people. Okay. So you people can refer. We'll see you on Friday. I'll get back to you on quantum error correction. Probably, if needed, I will check a little bit on Dutch Joyce algorithm. So Dutch algorithm and Dutch Joyce algorithms, in a way, a base for all the quantum algorithms. Okay. Thank you for your attention. I'll stop at this point and over to the organizers.
Thank you, sir. As we come to the closure of today's session, our heartfelt gratitude to Dr. H. Aswath Babu, sir, for once again enlightening us with his expertise in quantum computing. Thanks to all the participants for your involvement. With gratitude to everyone, we look forward to carrying the insights gained today into our future learning and research journeys. Thank you so much.
You're welcome.
Participants kindly fill the feedback, and second quiz is also posted in the chat box.
Madam, can you please share me the feedback? I will also like to correct myself if there is any feedback there.
Sure, sir. I will share, sir.
Yeah, thank you, thank you. And also the Google, YouTube link you said it will be done on YouTube, na? Okay.
Yes, sir. Yes, sir. Yes,
So
sir. I
so please
will send
share the. I just want to see how it has come, the recording.
both recording as well as feedback. Both I will send you to your WhatsApp and as well as email, sir.
Yes, ma'am. So I will share my hand notes and yesterday's yesterday presentation, everything to you on the WhatsApp so that you can share with the. Okay, bye bye. See you, everyone.
Thank you, sir.
The mail ID, yes, I have. I'm just sharing on my WhatsApp. Sorry, in your chat.
Madam, Chandrasekhar ma'am, hello.
Yes, sir.
Ma'am, actually, quiz 2 ஒன்னு போட்டிருக்கீங்க and then another one is Sairam institution feedback, but both will come only quiz 2 தான் ma'am வருது, feedback வரலையே.
Just a minute, I will check.
Yes ma'am, yes ma'am. Thank you, thank you.
Thank you very much, everyone. See you on Saturday. Bye bye.